Okay, so our first example of using the trapezoidal rule. So let's put this into what it actually looks like. You guys may not know yet what the log curve looks like. I think you probably did do it last year. But the log curve goes just something like that. That's y, that's x. That's y equals log x, and that's base e. We've talked about that in class before. And it goes through the point 1 there, 1, 0, and if you look at the integral here, they want it from 1 up to x equals 4. So they want to find the area under this curve from 1 to 4. That's what this terminology means. Okay, so they're the x values. You've got the function itself, and that's the height, which we've been looking at, isn't it? That's the height, if we sub that in, times dx, which is the width. So when we actually go and do integration with primitives, that's the sort of terminology we're looking at. But at the moment, we're doing a trapezoidal rule, and it says 3 subintervals. Now, we've got the word subintervals, and that means sections. We've got the word ordinates, which are just the lines. We'll do some like that later on. So if it says 3 ordinates, there'd be 1 there, 1 there, and 1 there. It's actually the lines. Subintervals actually means, like here we've got 1 subinterval, 1 section. They can also use the terminology 3 trapezia. That's the same as subintervals. Sections, etc. So we have to get used to the different terminology. Alrighty, so what they're saying is using 3 subintervals. Now how do I know where on the axis to put my other 2x values? Well, if you remember from the last video, h, that distance of each trapezia, the height, was equal to the last x value minus the first x value over how many is required. And in this case, there's 3. So this is going to go over 3, which is 3 over 3, which means each h is 1. So 2 and 3. 2 and 3. So there's 1, and there's another 1. So that's our trapezia. So does that make sense? There's 1 subinterval. There's another subinterval, that's 2. And there's the third subinterval, that's 3. So we're just basically finding the area of those 3 trapezia. But the formula, should we do it over here? Area equals, now in blue, I'm just going to name them like we did. That's the first, that's the last, and that's y1 and y2. I'd really rather say yf, y first, and y last. So we're going to start doing that, even though you may not see that in the book. Just makes it, I think, a little bit more clear. So the formula was h on 2 into the first plus the last, y first, plus y last, plus 2 of everything else. Well, that's y1 plus y2 added up, because we're going to use this one twice for this trapezia, and then this one twice. Okie dokie. Now what we haven't done is these y's are actually the height of each side of these trapezia. So we need to sub in these x values into the function and get a y value. So let's do that first. So x equals 1, 2, 3, and 4. That's going to be the height, or sorry, the side of the trapezia. So log 1, log 2, just sub it into the function. Log 3 and log 4. Now, the question doesn't give any specification as to approximation. So what I mean is, if I left it as log 1, log 2, etc., that's exact. If it says to 1 decimal place, then I've got to sub it into the calculator. So I'm going to do that today. I'm going to sub it into the calculator, and we'll do it to 1 decimal place. So log 1, and you guys don't know this yet, but log 1 is 0. Log 2 is 0.69. And log 3, 1.099. I'll take that to 3 there. 099. And log 4, 1.386. Okay. So that's 0. We can see the height of that is 0. Okay, there is no height there of that one. That's 0.69, that's 1.09 and 1.386. So you can see that's correct in terms of this curve. You don't need to know what the curve looks like, but in this case we do, so we may as well use it. So if we sub all that into the formula, the area from 1 to 4 is equal to h on 2, I'll rewrite the formula, y first plus y last, I put those in brackets, plus the sum of 2 lots of the sum of everything else. In this case, the everything else is only y1 and y2. So that's our 4 values. Whoa. Not sure what happened there. Equals. H was 1. That's on the x-axis there. The first y value was 0. The last y0 value was 1.386. And the other two are 0.69 and 1.099. So then it's just a calculator exercise, working that out. So I've got a half into 1.386, if I work that out, plus 2 into 1.789. It's a shame, hey? 789. Poor old number 9. Bet number 10's scared. Okay, and we keep going. You may laugh. So 2 lots of that gives us 1.386 plus 3.578. That's 1.386. So that's a half times 4.964, and of course you can do all this in one hit on your calculator. I'm just taking you through it. 2.482. So to 1 decimal place, which is what we said, it's equal to 2.5, and our unit is unit squared. It's not centimetres or anything else, it's simply unit squared. So it's approximately equal to that. And of course if I took more trapezia, it would get closer to the real area.